Hey everyone, and welcome to The Explainer. There's this family of chemical compounds that are pretty much everywhere, from the medicine cabinet to the materials that literally built our modern world. We're talking about haloalkanes and haloarenes. And believe me, their story is wild. It's got heroes and villains all rolled into one.
Okay, let's kick things off with a little puzzle. Think about it. What on earth connects a cure for typhoid, a powerful malaria treatment, and modern surgery? They sound completely unrelated, right? But they all share one secret ingredient. Any guesses?
All right, the answer is a very special class of chemical compounds. Yep, every single one of those lifesavers, chloramphenicol for typhoid, chloroquine for malaria, halothane for anesthesia, they all have a halogen atom tucked inside. It's this tiny little addition that completely transforms them, turning them into medical powerhouses. So, who are these key players really? Let's pull back the curtain and meet these hidden halogens. Okay, so the basic idea is actually super simple. You take a regular hydrocarbon, think of it as a basic Lego structure, then you just pop off a hydrogen atom and snap on a halogen atom instead. And boom, you've just made a haloalkane or a haloarene. It sounds like a tiny change, but trust me, it opens up a whole new world of possibilities. All right, so we have this huge new family of molecules. How do chemists even begin to organize them? Well, it's all about looking at the blueprint, specifically where that halogen atom ends up. And this is where it gets really interesting. It all comes down to the type of carbon the halogen is attached to. For haloalkanes, it's attached to what we call an sp3 carbon, basically a carbon atom that's happy with all its single bonds. But for haloarenes, the halogen is attached to an sp2 carbon, which is part of a super stable aromatic ring, like benzene. Now that might sound like just some chemistry jargon, but that single difference, sp3 versus sp2, changes literally everything about how the molecule behaves. It's a total game changer. So with all these different structures, how do we keep them straight? Well, chemists have a sort of secret code, a universal language called the IUPAC system. A name like 2-bromo-3-methylbutane might look complicated, but it's not just a name. It's a map. It tells you exactly what the molecule looks like. Butane means a 4-carbon chain. 2-bromo tells you the bromine is on the second carbon. You get the idea. It's a perfect blueprint. So, what's their secret? What gives these molecules their special power, their chemical personality? It all boils down to one little thing: the polar bond. Okay, let's zoom in to the atomic level. Picture this. You've got a carbon atom and a halogen atom bonded together. Now, halogens are super electronegative, which is just a fancy way of saying they're really greedy for electrons. So, in that bond, there's a constant tug of war over the electrons, and the halogen is always winning. This pull creates a slight negative charge on the halogen and a slight positive charge on the carbon. And it's this tiny imbalance that makes the whole molecule reactive and ready for action. And you can totally see this in the numbers. Look at the trend here. As you go down the group from fluorine to iodine, the halogen atoms just get bigger and bigger. So naturally, the bond between carbon and the halogen gets longer and weaker. See that bond enthalpy? That's just the energy it takes to break the bond. The lower the number, the weaker the bond. And a weaker bond, well, that's an invitation for other chemicals to come in and react. And this polarity doesn't just affect reactions, it changes their physical properties too. Think of it like tiny little magnets. Because of those partial positive and negative charges, the molecules are more sticky. They're attracted to each other. So you need to crank up the heat a lot more to get them to boil and separate. That's why they have much higher boiling points than the plain old hydrocarbons they come from. Okay, so we've established that this polar bond makes these molecules itching for a reaction. So let's put them in motion and see what happens. We're about to dive into their go-to chemical move, and you'll see how things can get, well, pretty complicated. All right, here it is. Their signature move is called nucleophilic substitution. Sounds complex, but here's the play-by-play. You have a nucleophile, which is just a molecule that's rich in electrons, and it spots that slightly positive carbon atom in the haloalkane. It sees an opportunity, swoops in, attacks the carbon, and boots the halogen out. It's a simple swap, but this one move is like a master key for chemists. It lets them turn haloalkanes into almost anything else they want to build. But wait, it gets deeper. It's not just about what gets swapped. It's about how. You see, in chemistry, shape is everything. The 3D arrangement of atoms is absolutely critical. And some molecules have this amazing property, a kind of handedness, that changes the entire story. This property is called chirality. The easiest way to think about it is to look at your own hands. They are perfect mirror images, right? But try to place your left hand perfectly on top of your right,
You can't. They're non-superimposable. Molecules can be the same way. We call these mirror image twins enantiomers. And this isn't just a fun fact. In medicine, it can be a matter of life and death. One hand could be a cure, while its mirror image could be useless or even harmful.
So for chemists making medicines, this is huge. Depending on how they run the reaction, two things can happen. They can get inversion, where the molecule's 3D shape completely flips inside out, seriously, just like an umbrella in a storm. Or they could get racemization, which is just a 50-50 mix of both the original shape and the flipped one. Being able to control this outcome is everything when you're trying to create a specific, safe drug. Okay, let's zoom back out from the microscopic level, because for all the good these molecules have done, their story, well, it's a classic double-edged sword. It's a story of both heroes and hazards. For decades, compounds with lots of halogens on them were hailed as miracle chemicals. I mean, think about it. Freons gave us refrigerators and air conditioning. DDT was a powerhouse insecticide that fought diseases. Carbon tet was a go-to solvent for everything. They were the rock stars of the chemical world, celebrated as these amazing inventions. But there was a massive catch. The very thing that made them so great, their stability, turned out to be their biggest flaw. As the research points out, these compounds are super resistant to breaking down. They just stick around. And when we say they stick around, we mean for a very long time. Once they're out in the environment, they don't really go away. And this has led to some huge global-scale problems. The most famous example, of course, is the hole in the ozone layer caused by CFCs. Yep, the same things as freons. Not to mention the widespread contamination of our planet's soil and water. So this brings us to a really important question, doesn't it? These molecules are the perfect example of the two faces of chemistry. On one hand, they're lifesavers. On the other, they can be environmental hazards. The big challenge for us now, for modern science, is to figure this out. How do we keep the good parts, the life-saving power, while engineering out the planetary damage? How do we find that balance?